Okay, so we are going over lesson 6.4, and it's called Cut by a Transversal, and we're solidifying understanding. So in the jumpstart, you guys are going to do this together as a group, so just remind me. So in today's lesson, you're going to be able to prove that a line drawn parallel to one of the sides of a triangle that intersects with other two sides divides the other two sides proportionally. And you're like, what does that mean? Don't worry, we'll talk about that. And then it says, what observations can I make about the segments formed on two sides of a triangle by a line drawn parallel to the third side? And what if a parallel line is below the base? How might I justify my observations algebraically? So it says, draw two intersecting transversals on a sheet of paper as in the following diagram. Label the point of intersection of the transversal A and select any two of the horizontal lines to form the third side of two different triangles. Label the endpoints of the third side of the smaller triangle B and C, and the endpoints of the third side D and E. So wait, what? So here's our thing, and I do want you to copy this on a piece of paper. It's best to use kind of that ruled paper so that you can just use the lines that go across and you don't have to draw them. So it says one more time, draw two intersecting transversal on a sheet of lined paper. They did that for you. They did that for you. It's these two lines here. And then it says, label the point of intersection of the transversals A. Okay, so going back to this picture, hold on a second, just scroll. They already labeled it A for me, right? So then it says select any two of the horizontal lines to form the third side of two different triangles. So you should see that there's this triangle here, right? And then because of that parallel side, and then there's going to be another triangle that looks like, this here, right? So those are your two triangles, the yellow one and the pink one. So then they just said label them. So they want you to label the endpoints of the third side of the smaller triangle, B and C. So that looks like this. B is here, C is here, and the larger triangle, D and E. And whenever we're labeling points, we always use capital letters, smaller letters or lowercase letters always indicate like the length of a side or a variable. All right, the question, what convinces you that the two triangles formed by the transversals and the horizontal lines are similar? Okay, note, we can assume the horizontal lines on a sheet of paper are parallel. So we learned about similarity, and I'll just remind you, from the last lesson, you learned AA triangle similarity, you learned SSS triangle similarity, and you learned SAS triangle similarity, which means if two angles of a triangle are congruent to two corresponding angles of another triangle, then those two triangles are automatically similar. Okay. Side, side, side is if all three sides of the triangles are proportional to all corresponding sides of the other triangle, then they're similar. Same thing goes with SAS, except for its two sets of sides are proportional, and the angle included, that's why A is in the middle, right? The A is in the middle. Then the A has to be in the middle of those two sides included, then the two triangles are similar. Okay. And so we know, because of our past learning, that when we have two lines that are parallel, that are cut by a transversal, we get all kinds of angles being congruent. Namely, in this case, we're going to choose that this angle is congruent to this angle. Similarly, I could say this angle on this right-hand side is congruent to this angle on the right-hand side. So because of that, those two triangles, triangle ABC is similar to triangle ADE because of AA similarity. Okay, so I'm going to write that down. So triangle ABC is similar to triangle. Now I have to go in the same order. I start with A. Who is B? Who does B match with in the bigger triangle? Okay, so hopefully you said D and E. These two triangles are similar by the AA triangle similarity. It's a postulate. That's fine. AA triangle similarity. Okay, and how did we prove that those two triangles, these two angles are congruent here? So these two angles here, so angles are congruent because corresponding angles of parallel lines are congruent. Okay. Okay, so that's my little quick proof. Okay, I didn't assume anything. All I did is I took the two triangles. I said, hey, since these two lines are parallel, I get that these two angles are congruent, and these two angles are congruent because their corresponding angles of parallel lines are congruent. Okay, and because I have two sets of angles congruent, then that means I have AA triangle similarity. So that means that those two triangles are similar. Okay. If that didn't make sense, draw it again and just remind yourself, oh, because these are parallel, what do I get? Oh, I get congruent angles. And if I get two sets of congruent angles, then I automatically win AA similarity. Okay. So let's do the next problem. It says, write some proportionality statements about the sides of the triangles that you have drawn, and then verify the proportionality statements by measuring the sides of the triangles. Okay, so I don't have a ruler, so you're going to have to do this part. Okay, so I'm going to write some proportionality statements, and there's a lot. Okay, there's a lot of them. So I'm going to write one set, and then I want you to find some more. So using that up there, I could say that AB over AD, so the left side of the smaller triangle over the left side of the bigger triangle is equal to the right side of the smaller triangle over the right side of the bigger triangle. And if I wanted to, I could also do that third side too, right? I could do the BC over DE, and I'll write that here. BC is over DE. So you don't need all three, like those three. I just wanted to write all three. So essentially, if you look, I could have written this statement and another statement. I could have written these two together. And if I wanted to, then I could write the first and the last together. Okay. All right. There's a couple of other ones that I want you to think about, but yeah. So there's a couple more. So go ahead and pause and see if you can write any more that you see there. Okay. Okay. All right. Now that you're back, it says select a third horizontal segment to form a third triangle that is similar to the other two. Write some more proportionality statements with those. And so all they're asking you to do is draw another line, maybe a third one up here, and then go ahead and label it A, B, C, D, E, F, G, and then go ahead and write some more, right? Okay. So Tristan has written the proportion for problem 3 based on this diagram, and he wrote BD over AB. BD over AB. Make it this small so I can see. So BD, that little part over AB, which is the big part of the triangle, is equal to CE, the little part, the extra little part, over AC, which is the whole triangle. And he says, Tia thinks Tristan's proportion is wrong because some of the segments of his proportion are not sides of a triangle. Okay, so check out Tristan's idea using the measurements of the segments in his diagram. So again, he said, I need to write it down so that you guys can see it. He wrote BD over AB equals to CE over AC. So check out his measurements and see if you agree. Okay, so you measured some stuff and then we're now moving forward. It says, now check out the same idea for yours. So they're basically saying this, and I just kind of want to highlight. They're saying BD, this little guy here, over AB, which is the whole side of the top triangle. I don't know why I'm not highlighting on the triangle. Sorry. Let's try that again. There you go. I can color. Just kidding. Is AB. And then we get CE, the little guy, over the small triangle's right side. That's what they're saying is in proportion. Okay. And so that's what you want to check. So based on this, what do you think? What does your gut tell you? Yes, they're in proportion, or no, they're not. What do you think? Okay. So now we're going to prove it, right? So Tia still isn't convinced. Since Tristan is basing his work on a single diagram, she decides to write a proportion that she knows is true. AD over AB, which is big triangle left side over little triangle left side, over is equal to big triangle right side and little triangle right side. Okay, so she knows that this is true. Okay, Tia realizes that she can rewrite this proportion. So instead of looking at AD, she could look at AB plus BD. And that's true, right? AD, this whole guy here, right? AD is AB, this pink part, plus the yellow part. So that's true, right? So it says, why is this true? So we know that these are true because, so we know this is true because these two triangles are similar because the two triangles are similar. And because they're similar, we know that the sides are proportional. We know sides are proportional. Okay. So we know that this is true because all we're doing is we're breaking up the big segment into two smaller segments. Okay. So we can call this the segment addition postulate. Okay. And so what the postulate is saying is part plus part equals whole. And I'll write that here. Part plus part equals whole. Okay. So can you use Tia's proportion to solve algebraically that Tristan is correct? So because they're telling us to prove something, that means that Tristan is correct. So for those of you who said that Tristan is correct, good job. So what we're going to do is we're going to start off with this one right here. AB plus BD over AB equals to AC plus CE over AC. Okay. So the first thing that I notice is that I could divide. And it looks weird because we're using like points and stuff and lengths. But what I'm going to do is I'm going to distribute the division for each one. So it's going to look like this. So AB over AB plus BD over AB. See how I distributed this division here and here? I just separated them. And I'm going to do the same thing over here. So AC over AC, plus, not equals, sorry, plus CE over AC. Does anybody see anything? Yeah, AB over AB is 1. So I'm going to make this a 1. And I see AC over AC is 1, right? So because both of those are 1s, I could subtract a 1 from both sides. So I'm going to subtract 1. Oops. I'm going to subtract 1 from both sides. And notice that cancels. Minus 1, 1 minus 1 is 0, right? AB divided by AB is 1. If you don't know why, just think about, take any number and divide it by itself. What do you always get? And the answer is 1, except for a 0. Okay, so I just like to do that. And then I'm going to write this last statement out here. It says, leaving these alone, I get BD over AB is equal to CE over AC. And that's what we originally sought to prove up here, right? That's what Tristan said. So Tristan was right. And I want you to check out that proportionality, right? I want you to be comfortable with that proportionality. So when you see this picture, and I call this like nested triangles, where they share an angle, right? They're nested. They're like put inside of each other. Do you remember like nesting toys? Like they fit inside each other really, really well. Or I really like my measuring cups for cooking. I have a 1 cup, and then I have a half a cup, and my half a cup fits inside of my 1 cup. So they nest inside each other. And then my 1/3 cup fits inside my 1/2 cup, which my 4th cup fits inside that, and so on and so forth, right? So these I call nesting triangles because they fit inside of each other. And so one of the first things I'll tell my students to do is, because they're stuck inside each other, I usually tell my students to draw them out again so that they're separated from each other. So there's a little bit more to see. So that's one of the key points that I tell my students to do, so that at least you'll be able to see the 2 triangle things going on there. Okay. So let's go over our takeaways so that you guys can move on to your ready, set, go and your exit ticket. So it says the triangle midline theorem is a special case of a theorem sometimes referred to as a side splitter theorem. Okay, so so in here we get we have a triangle, and we get these sides that are parallel. So the side splitter theorem, if you remember it, was when we connected the midpoints of 2 triangles, and we got proportional, and this was like half of it, right? So here are some, so given that UV is parallel to WX and parallel to YZ and parallel to RT, what are some proportionality statements? Okay, so you should be able to mark some of these out. I'll write some of them with you. You could say something like UW over wy is equal to, no, I did this little section over this little section, right? So then what would be on the other side of this? What do you think would be on the other side of this equation? What actually has to be on the other side of this? Hopefully you said Vx over xz. Okay, that's one of them that you could say. Another one that you could do is you could do UW over YR, UW over YR, and what would have to be on the other side of that? UW over YR, excuse me. What has to be on the other side? UW. Who matches up with UW? And you're like, oh, VX. Okay, good. VX. And who matches up with YR? And hopefully you said ZT. And there's quite a few more that you could do, right? Don't limit yourself. I could even talk about WR, and you're like, Miss Johnson, you're skipping over Y. That's fine, right? So make sure that you're comfortable with this one. This was a pretty short lesson, but now you can look at all those things and make sure that you're comfortable with them. Make sure you read the lesson summary, because that's a really good place to kind of like pull your thoughts together and make sure that you got what you understood. All right. Thanks for listening. Have a great day.